Swayam Prabha. Digital India. Educated India.
Let us understand the armature reaction in DC generator. Armature reaction in DC generator. So normally what happens when a field is being produced by the field windings, it produces a magnetic flux or the magnetic field in the machine that induces the current. That induces the voltage which feeds the load and supply the current. That's what the generator does. Now there are two currents. One is the field current and there is the armature current. So when we talk about the field current, the armature current when comes into the picture, it produces a reaction field, so which can add or which can oppose the effect of the main field winding. This we are going to see that under the topic of armature reaction. So armature reaction is the effect of magnetic flux set up by the armature current upon the distribution of flux under the main poles. So what is the armature reaction? Armature reaction is the effect of magnetic flux set up by armature current upon the distribution of flux under main pole. On the distribution of flux under the main poles. Okay. So to understand this, first let us understand that what is the distribution of the main pole field. Okay. So considering this is a rotor and on the there are two poles. Okay. So here in case you'll be having a two poles, so you can get this as a north pole and this is a south pole. Okay, and the north pole, if you see, there'll be like windings here. So these are basically the coils of the wire. So that will be the dotted one and that will be the cross one. Okay, so that will get the flux in the direction of north to south. In this case, these are the cross and these are the dots. So you'll get the field lines. Okay, and the machine is rotating this way. Suppose the brush is connected here, one brush is here and this is another brush. Okay, and there is an axis. So in this axis, if you see, this is the geometrical axis, right? We call it as a geometrically neutral axis and the magnetic neutral axis. So in the case of So there exists an MMF of the main poles which produces the main flux. So the MMF of these poles produce a main flux, and the field lines are given here in this direction. And these slots, the rotor is having slots in which there are conductors placed. Okay. There are conductors. So now this is how the main pole magnetic flux distribution will be in case of a machine. This is main pole magnetic flux distribution. Magnetic flux distribution. Okay. Now the main point in this case is that the magnetic neutral axis. So this axis is magnetic neutral axis and geometrical neutral axis. So the magnetic neutral axis MNA is a plane perpendicular to the axis of flux. Is a plane perpendicular to the axis of field. Okay. Then we will be having a geometrically neutral axis, which is also the same as the magnetic neutral axis in this case. So under this condition, it coincides with the geometrical neutral axis. So the magnetic neutral axis is called as the axis of commutation. So this is also known as axis of commutation. Okay, so this is the effect when there is no armature current. Okay, so there is no armature current when so if we have the same kind of arrangement. Okay, so let us draw this arrangement line, just copying this and paste, suppose here. And now what I'll do, I'll remove this magnetic field which is due to the now if we have the conductors, suppose this side conductors are the cross one, the conductor is going inside, the current direction is such a way, and this side the conductors are coming up, the current is, this is the direction of the current. Okay, so now the field here will be of this nature, correct? Or what I'll do, I'll change the color so that we can see it clearly. So the field lines will be this kind of field lines will be coming in the direction, if you calculate, it will be in this direction. Okay, so these field lines are The red color field lines are armature flux distribution. In this case, the field windings are neutralized. I mean, they are not excited. So there is no field, only the current are present in the armature conductors. Now, if you add these two, okay, if you add these two and these values, you will see that these values will get added up one side and get subtracted on the other side. Okay, so it will be so the resultant, if you draw, it will go to little tilted direction. Okay, and this will be the magnetic neutral axis now. So this is basically the addition of the two, which can be written as resultant flux distribution. This is the armature reaction. So you can see that when there is a current in the field windings and the current in the magnetic the armature conductor, so the resultant field will get some inclination. The phi r is the resultant thing. So if you see, the main flux will be horizontal direction, which is here in this case, and you will have an armature current which is perpendicular, and then you will get the resultant phi r. This is phi main, which is here. This is phi main, and the phi armature, which is phi a. So this is phi a, and the perpendicular axis to this is this. So this is perpendicular thing. So this is geometrically neutral axis, and this is new magnetic neutral axis. So you can see there is a tilt. Okay, so earlier both were coinciding. Now the MNA and GNA are not coinciding. So this effect is known as the armature reaction. So the conductors combine their MMF to produce a flux through the armature in the downward direction, here in this case. Okay, so the conductors on the right hand side of the armature carries a current in the direction out of the paper. So this is the assumption which we have taken, and the flux phi a is represented the direction in clockwise in this section and anti-clockwise in this section, and this is the phi r, the resultant flux. Okay, so you can write down this theory in the statements and you can understand what is the effect of armature current on the main field flux. So if we consider the field, the nonlinear behavior in the saturation of the core, okay, then the increase in the flux one pole tip, and then the decrease in the flux on the other pole tip, and subsequently the main pole flux is decreased, since the reduction in the flux of the terminal voltage of the generator will increase with the load. So the idea is basically, the more the load current, the more will be the armature reaction. Okay, so what are the effect of armature reaction? What are you understanding and what you can think of as a effect? So we can just note down the effects of armature reaction. What are the effect of armature reaction? First is that magnetic flux density increased over one half of the pole and decreased on the other half of the pole. So you can see the magnetic flux density is not uniform over full pole shoe. Okay, it's not uniform over full pole shoe. So it is increased over one half of the pole and decreased over other half of the pole. Okay, but the total flux produced by the each pole is slightly reduced, and total flux per pole is slightly reduced. So this effect of total flux reduction by the armature reaction is known as the demagnetizing effect. So this reduction of total flux due to armature reaction known as demagnetizing effect. Okay, the flux wave is distorted and the shift of the position of the magnetic neutral axis in the direction of rotation for the generator and against the direction of rotation for the motor. So the tilt of this axis will be depending upon the type of current which is flowing. Basically it is going to the armature or coming out of the armature, or the motor operation or the generator operation, correct? So the flux wave form is distorted. Flux waveform is distorted and there is a shift in the position of magnetic neutral axis. Shift in the position of magnetic neutral axis. So for generator, the shift is in the direction of rotation. And for motor, the shift is opposite to the direction of rotation. Okay, so this is the effect of armature reaction. One of the main part which you can see that it produces the field. Okay, so here it was neutral earlier. If you see, this is the neutral zone, but in this case the neutral zone will be having some field due to the armature reaction. So one of the point is that it establishes flux in the neutral zone. In the neutral zone. What it does, it induces the some other voltages which aggravates to the commutation problem that leads to commutation problem. Okay, so this is the total main effects of the armature reaction, which we can understand from the effect. So with that armature reaction, now we can understand the effect of commutation, how the effect of commutation can be considered, and then we'll see the role of commutating poles and interpoles, why they are used, and then we'll go to the characteristics. Okay, so this is the idea. So let us first understand the commutation. Okay, so commutation is basically the process of getting a DC output terminals at the terminals, right? So the current induced in the armature conductors of a DC generator are AC in nature. As I told, because of the north and south pole, the polarity will keep on changing. So the armature current will be having armature current is having AC variation, and the commutation is needed to convert that AC. So the commutation process involves the change from a generated AC into the applied DC current. So the induced current flow in one direction when the armature conductors are under the north pole, and it changes to the other direction when it goes under the influence of the south pole. So this is the deal. So as the conductor, so suppose there are conductors, right? So you can draw a kind of loops or the conductors. So I'm just trying to draw some turns of a winding which are supposed to be commutated. This is the winding which is on the rotor. Okay, so this is basically the terminal, the contacts. Okay, so these are insulated from each other. These sections are insulated from each other, and when there is a, so this touches this point. Okay, there is a contact here which is basically the electrical contact, and what will happen, the current which is suppose coming in this direction has to go to this direction. Okay, so now the same current will be coming here and then going here, coming here, and then going to the top. So this is how the motion of the winding will be there. So this is the rotation, direction of rotation. So this is basically rotating, and the position of the brush. Okay, so the brush, you can assume that is here. So this is the brush position. Okay, so what will happen, if you see clearly, this loop gets shorted. Okay, so that current which is coming here and this current which is coming here will go in this direction. So what will happen, this will become short. So this current which is I flowing here is not going here because it is getting shorted, so it will be coming here I, and then one current from the opposite direction will also appear here. Okay, so this will come here, so it will be 2I. Getting the point? So this will be shorted, so no current will be going in this part. So one current I here, one current I here. So this is basically the 2I. Now similarly, if this moves to the next coil, so what will happen if it comes here? So let us copy paste this section. Okay, so what will happen, I'll just remove this. And now the position is this, the brush moves to this position. When the brush is here, what do you expect? So the current which is coming here, so this current and this current, total current is coming here, 2I. Correct. So the same current from this side and this side is being collected by this brush. This is brush. Now after some time, this will move to the next position. So what will happen? This will move to the next position here. Under this condition, this will get shorted, so this will not be having any current. And one current I will be going here, and this current will be coming from here. So here again it will be 2I. And similarly it will keep on happening. So this will be keep on moving, and this brush will be collecting the current either on this or this section or the both, where you can clearly see that the current 2I is maintained in the same direction. So this current 2I is known as the DC current. Okay. So if you draw the coil current as a function, so initially you will be having positive I, then it will go to the negative I, and this is the commutation transition. So if the characteristic is like this, then this is known as delayed or under commutation. Or if it is like this, then this is known as the over commutation. So this is basically the characteristic with respect to the time and the current. Okay, so this is the characteristic. Now if here in this particular case, if we see the cause of sparking, that is basically the failure of the current in the short circuit element to reach the full value in the reverse direction by the end of short circuit time. So if this is not maintained, so there will be sparking at this kind of junction. So you'll be seeing when motor is running, you see that at the brush terminal there is always spark is happening. So that is because of the commutation failure. Okay, so this is the idea of commutation. So with the movement of the winding, the terminal at the commutator and the brush collection, okay, so that position which you can see from here, which is insulated at this junction, so when it moves slides on this commutator, then there is a sparking due to the improper commutation. So there are various methods which can be used to improve the commutation, basically to avoid the current. So that is on the resistance commutation, voltage commutation, or compensating windings, which are being used for commutation problems. So commutating poles or interpoles are used for the commutation problems. So you can read in the reference books where the interpoles are the narrow poles which are being constituted inside the machine in between the main poles. So the idea of those poles is to basically provide a magnetic field in such a way that the uniformity of the magnetic field at the pole shoe happens, which was due to the reaction of magnetic this magnetic neutral axis and geometrical neutral axis difference. So that difference if we can reduce, then we can have a better commutation problems. So we have a demagnetizing winding to if get the effect of or we also known as the compensating winding for the effect of armature reaction, so that we can avoid the problems of sparking. So the compensating windings are most effective means of eliminating the problems due to the armature reaction. Okay, so the issues which was there, which we have mentioned, the compensating windings. Okay, so first we'll write the effect or the sparking issues. Okay, so normally what happens when the actual practice, the current in the short circuit coil after commutation period does not reach to its full value, and this is due to the fact that the short circuit coils offer the self inductance. Okay, so there is a delay in the, or there is a rate of rise which appears, and it cannot suddenly jump from any value to any value. So the rate of change of the current is such that there is a back EMF which is being takes time, or the reversal of the current. Okay, so that large voltage appearing between the commutator segment due to LDI by dt, and also causes the spark at the brushes. Okay, so the insulation is not adequate to take care of that much of the potential loss due to LDI by dt. Okay, now if we have the how can we provide the method to avoid this commutation problem? So the commutation problem can be handled by three methods. So methods to improve commutation. Okay, we'll not go to that detail, but I'll just tell you the resistance commutation. In the case of resistance commutation, so what happens, we provide a resistance, physical resistance between the commutator segments and the brush, so that the high resistance has a tendency to force the current in the short circuit coil to change according to the compensating requirement. So that's why it is known as the resistance commutation. The second is the voltage commutation. Okay, so in case of the voltage commutation, the arrangement is made to introduce a voltage in the coil which is undergoing the commutation that will neutralize the reactance voltage. So the reactance voltage was the voltage which is generated due to the inductance, self-inductance of the turn which is going under commutation. So that high LDI by dt voltage will be generating. So by induce the opposite polarity voltage of LDI by dt, or the self-induced voltage which is the reactance voltage, we use voltage commutation technique. And the third one, the most commonly used, is the interpoles. Okay, so that voltage basically is, or we can write compensating winding. So that difference appears due to the armature reaction, right? So that difference, armature winding, it will take care of the armature reaction. So you get the uniformity of the magnetic flux, magnetic neutral axis and the geometrically neutral axis. So it improves the commutation. So these are the few techniques by which, let us consider the characteristic of a DC generator now. Okay, so let us consider the characteristics of DC generator. So at present the bulk of the electrical energy which is being generated is in the form of AC, but the DC generators are also used for a specific application. So we'll be having three characteristics. First one is the magnetization characteristic. Okay, so in this characteristic, which gives the variation of the generated voltage or the no load voltage with the field current. Okay, so this is the EMF with field current is IF. So this is a magnetizing characteristic. Then we'll be seeing for the different kind of machines. So the second characteristic is internal characteristic. Internal characteristic. Internal characteristic is the plot between the generated voltage and the load current, E and IA. And the third characteristic is the external characteristic. Which is between the terminal voltage and the load current, V and IL. So let us consider the separately excited DC generator. Okay. So now if you see the effect of separately excited DC generator. In this particular case, suppose you have the armature resistance and the motor here, which is the armature generator, and it is supplying to some load, which is a variable load. Okay, so this is IL, this is VL or V, will not get confused. So this is V, this is E, this is RA, and this is IA, and this is separately excited, right? So this is IF. Okay, so now the total the field voltage is nothing but IF into RF, and EA, the terminal voltage, if you see from here, it is nothing but V plus I into RA, and EA is also a function of some constant into pi into omega m, and the load voltage V is nothing but IL into RL, so this is RL. Okay, and here in this case IA is equal to IL. So now there is no armature reaction, the generated voltage V0 would be constant and it will be shown by the straight line. So let us draw the characteristic now. So this is the ideal voltage generated. Okay, V0. This is IL or the IA. Here in this case both are same. This is, and IL into VL is the load characteristic. This is load characteristic. Okay. So when you consider the internal characteristic, there will be a drop of which is across the resistance. So if you see, this will be like one drop and one will be this way. And this is your operating point. This is your external characteristic. External, and this drop, if you see, if you zoom this portion, okay, so one line is here, one is here, and one is here. So this portion V0, so this is the zoom portion, delta V armature reaction की वजह से the drop, and then we have this point P, I into RA. This is a operating point, and this voltage is known as a V, and this is V0. Okay, so this is the characteristic which you can find from this equation. This is internal characteristic. This is ideal. Ideal means there is no armature reaction or anything else. Okay, so these are the characteristics from the generating point. So with that, we would like to finish this generator part. Next section we will be seeing the motors and some motor characteristic which are being drawn from the electrical equivalent circuit of the motor. So with that, we'll just close this chapter.